Now we will discuss how to implement sequence alignment in a more efficient way. Usually we compare quite long sequences up to few tens of thousands of amino acids, and runtime of alignment algorithms, as you know, is proportional to the number of edges, which is quadratic, and memory consumption of alignment algorithm is also proportional to the number of nodes, which is also quadratic. And memory is often bottleneck, because on runtime you can execute billions of operations in 1 second, but to store billions of values in memory you need one or few gigabytes of memory. And if you want to compare longer and longer sequences, you still can wait for many seconds while your algorithms try to compute this alignment, but you don't have such huge amount of memory which is needed for algorithms. So how can we do this? Let's define middle column of our Manhattan grid as a column in the middle, so it's quite simple, and we define middle node in the Manhattan grid as a node where an optimal alignment path crosses the middle column. For example, in this grid we have this highlighted node as a middle node, because our optimal paths go through this node, and this node is in the middle column. Let's design an algorithm to find sequence alignment. At first step, we need to find a middle node. Then we need to find alignment between the source and middle node. And after that, we need to find alignment between middle node and the sink. Since we know all parts of a path, we can do it recursively. So the only problem is how to find this middle node, because we don't know yet. Let's first discuss how to find alignment score in linear space. Previously, we used backtracking pointers to find longest path, and it required quadratic memory. But what if we don't need this longest path, but we want to know only score of alignment? Can we skip storing these backtracking pointers and use less memory just to find alignment score without alignment itself? Let's take a look on our Manhattan grid. And we have a first column, and we know all values in the first column. After that, we can compute all scores in the second column using the first column values only. And that's the same as we previously discussed when describing alignment algorithm. But for the third column, we don't need to know values of the first column, and we can simply forget them and reuse this memory, because for the third column we can use only scores from the second column, and so on and so on and so on. And at each moment of these algorithms we need to store only 2 columns, and we don't need to store all scores of all nodes in our Manhattan grid. And now we know how to find alignment score in linear space, but we want to find all alignment in linear time. And let's go back to our middle column and middle node. So middle column was a column in the middle, and middle node was a node where optimal path crosses this middle column. Let's define I path as the longest path among all paths that visit ith node in the middle column. And for example, length of 0 path is 2 here, and length of 4 path is 4. And let's try to compute these numbers, length of all I passes in the middle column. For example, here in this graph it's 2, 3, 3, 4, 3, and 1. And 4, our middle node, is a maximum node in this vector of length of I passes. So length of I pass, which we will write down as length of I, is consists of from source I and to sink I, which is 2 parts of our path, from source to this node and from this node to the sink. And we can find all values from source i's just by going through the first part of Manhattan grid using our linear space algorithm to calculate alignment scores without alignments itself. And we also can find vector of values from sink by going in the second part of Manhattan grid, but backwards. So we will start at our sink and we will go by backward edges trying to reach this middle column, also in linear space. So we will know alignment scores, but we won't know alignments which led to these scores. And after we have these two vectors from source and to sink, we can sum them up and find values in a middle column. So what is the runtime of this algorithm? So to find from source, we need to visit area divided by 2 of our whole Manhattan grid. And to find to sink vector of values, we need to also visit area divided by 2. So we actually need to visit whole Manhattan grid to find values in a middle node. So isn't it too large? Using the same runtime as before, we found only middle node. So we found only single node which belongs to our optimal path, and it required quadratic time. So what can we do next? We can split our Manhattan grid into 4 parts, and highlighted parts here should be visited after we found middle node, because our optimal path stay somewhere in these areas. But we can skip other 2 areas from our considerations on the next steps of algorithms. So on each of these highlighted parts, we need to find middle node. How many time will it take? The area of this node is proportional to the half of our area of whole Manhattan grid. So we need only half of the time which were required to find single middle node to find 2 more middle nodes in these separated areas. So after this step, we will have 3 nodes which belongs to our optimal alignment path, and we can iterate more and more. So on the next step, we will split our area into smaller rectangles, and we will find middle node in each rectangle, and so on and so forth. And on a third level of recursion, the total area which we need to take a look on is proportional to the area divided by 4, and on the 4th step it's even smaller and smaller, and during the whole algorithm, firstly we visited whole area to find single middle node. In the next step, we visited area divided by 2 to find more nodes on our optimal alignment path, and on the next step we visited area divided by 4, and so on and so on. And this progression sum up to 2 times area. So it's actually linear runtime of these algorithms, linear by area of our Manhattan grid. You can see the illustration here. For example, for the first pass, we need to take a look on one area. On the second pass, we need to take a look on a half of area. And on the third pass, it's fourth, and so on and so on. And you can easily take a look here that it sum up to 2. So what have we done? We designed algorithm which required only linear space, because every step in this recursion requires linear space to find a middle node in a given area. and runtime of these algorithms is still linear to the our number of nodes and number of edges in an alignment graph. And by using this technique, it's a little bit slower, but by using this technique, we can slow down a little bit of runtime, but still find whole alignment in linear space.